Ever tried sending a message through a crowded subway? The more people in the way, the more likely your message gets lost or distorted. That's kind of what happens in graph neural networks, those powerful AI systems that learn from relationships in data. But here's the catch. When information has to travel far across a network, it can get squashed, losing critical details. Today, we're diving into a breakthrough that uses math's favorite concept, curvature, to fix this problem. Let's start with the basics. Graphs are like digital maps of connections. Think social networks, biological systems, or even the internet. Nodes dots represent entities and edges lines show relationships. But here's the issue. Traditional graphs can't handle complex, multi-way interactions very well. Imagine trying to model a group chat where everyone talks at once. Pairwise connections just don't cut it. This is where oversquashing comes in. In graph neural networks, information flows between nodes through edges. But when messages have to travel long distances or pass through narrow bottlenecks, they get compressed into fixed-size representations. It's like trying to fit a whole conversation into a single tweet. Important details vanish. Researchers call this loss of sensitivity oversquashing, and it's a big hurdle for AI systems trying to understand complex networks. So how do we solve this? The answer lies in geometry. Specifically, a concept called Forman-Ricci curvature, a way to measure how bendy a graph is. Think of it like assessing the shape of a landscape. In continuous spaces, curvature tells us if a surface is flat, curved, or saddle-shaped. On graphs, it helps identify key structural features, clusters of tightly connected nodes, like social circles, and the bridges that link them. Here's the clever part. By analyzing curvature, researchers can spot where information bottlenecks occur. They then use this insight to lift the graph into a more complex structure called a hypergraph. In a hypergraph, a single hyperedge can connect multiple nodes at once, like turning a group chat into a single message thread instead of individual texts. This shortens the distance between important nodes, preserving information flow across the network. The result? A smarter way to handle long-range dependencies. By treating network backbones as hyperedges, the model avoids squashing critical data. It's like adding express lanes to a highway, ensuring messages reach their destination without getting lost in the traffic. This approach isn't just theoretical. It's a practical step forward for AI systems dealing with real-world networks, from understanding protein interactions to improving recommendation algorithms. By blending geometry with machine learning, researchers are paving the way for more robust and efficient graph-based models. Now let's get technical. Forman-Ricci curvature isn't just a number, it's a lens to rebuild the network itself. Imagine two busy highways, high-degree nodes meeting at an intersection. The curvature there might be negative, a sign of potential congestion. Conversely, if two less connected nodes link up, the curvature is closer to zero, like a quiet backroad. This metric helps identify which edges are critical for information flow and which are bottlenecks. By analyzing these curvature values, researchers create hypergraphs that separate edges into clusters, tight groups and long-range interactions, distant connections. For example, a hyperedge might link a group of friends who all share a mutual connection, capturing complex relationships that simple lines can't. This structure allows models to better understand how information, diseases, or ideas spread through a system. The proof: experiments on real-world data. When researchers applied this method to tasks like classifying molecules or analyzing proteins, models like EDGNN and GAT saw significant improvements. In 75% of cases, the curvature-upgraded networks outperformed the original. Even more advanced models like EDGNN and EDGNN2 showed gains in 80% of tests. So why does this matter? It's about seeing beyond the obvious. By reimagining networks through curvature, we're not just mapping connections, we're uncovering the hidden geometry of complexity. Whether it's predicting drug interactions or optimizing social media algorithms, this approach opens new doors for AI to tackle problems we've never solved before. Next time you see a network, think, what's the curvature here? It might just reveal the key to unlocking its secrets.